Welcome to this Class 10 Physics lecture on the effects of electric current. Electric current is defined as the rate of flow of electric charge through a cross-section of a conductor. Historically, current was considered to be the flow of positive charges, which is why conventional current is defined from positive to negative terminals, opposite to the actual flow of electrons. For a current to flow, we need a closed-loop circuit and a potential difference, which is the work done to move a unit charge from one point to another. In this slide, we see a basic circuit loop with a voltage source driving electrons, creating a steady electric current. Ohm's law is the foundation of electric circuit analysis. It states that the electric current flowing through a metallic conductor is directly proportional to the potential difference across its terminals, provided its temperature and other physical conditions remain constant. Mathematically, V equals I times R, where R is the constant of proportionality called resistance. Resistance is the property of a conductor to oppose the flow of charges through it, measured in ohms. We define 1 ohm as the resistance of a conductor when a potential difference of 1 volt produces a current of 1 ampere through it. The resistance of a conductor depends on three main factors. First, it is directly proportional to the length of the conductor, as longer paths present more collisions for electrons. Second, it is inversely proportional to the cross-sectional area, as wider paths provide more space for charge transit. Third, it depends on the nature of the material. Combining these, we write resistance R equals ρ times L over A, where ρ is a constant called electrical resistivity, measured in ohm-meters. Resistivity is a characteristic property of a material. Metals have very low resistivity, whereas insulators have extremely high resistivity. When two or more resistors are joined end-to-end consecutively, they are said to be connected in series. In a series combination, the current flowing through each resistor remains exactly the same, while the total potential difference across the combination is equal to the sum of the individual potential differences across each resistor. Therefore, the equivalent resistance of a series combination, Rs, is equal to the simple sum of the individual resistances, R1 plus, R2 plus, R3. Connecting resistors in series always increases the overall resistance of the circuit, reducing the total current. When resistors are connected across the same two common nodes, they are said to be in a parallel combination. In a parallel circuit, the potential difference across each resistor is identical, while the total current entering the junction divides among the parallel branches. The reciprocal of the equivalent resistance, Rp, is equal to the sum of the reciprocals of the individual resistances, 1 over R1 plus 1 over R2 plus 1 over R3. Connecting resistors in parallel always results in an equivalent resistance that is smaller than the smallest individual resistance, which increases total circuit current. When an electric current passes through a purely resistive conductor, the electrical energy is entirely converted into heat energy. This is known as the heating effect of electric current, or Joule heating. Joule's law of heating states that the heat produced in a resistor is directly proportional to the square of the current, directly proportional to the resistance, and directly proportional to the time for which the current flows. The formula is expressed as H equals I squared times R times T. Practical applications include domestic appliances like electric irons, heaters, toasters, and security devices like electric fuses which melt to break circuits during overloads. Electric power is the rate at which electrical energy is consumed or dissipated in an electric circuit. It is represented by the symbol P and is measured in watts. Power can be calculated as potential difference V times current I, or as I squared times R, or as V squared over R. 1. What is the power consumed by a device that carries a current of 1 ampere when operated at a potential difference of 1 volt? The commercial unit of electrical energy is the kilowatt-hour, commonly referred to as a unit, which is equal to 3.6 million joules. A magnetic field is the region around a magnet or a current-carrying conductor where magnetic forces can be detected. Magnetic field lines are imaginary curves used to represent the strength and direction of a magnetic field. By convention, magnetic field lines emerge from the North Pole and enter the South Pole outside a magnet, forming continuous closed loops. The closeness of the field lines indicates the relative strength of the magnetic field. Where lines are crowded, the field is strong. Two magnetic field lines can never intersect, because if they did, a compass needle would point in two different directions at the intersection, which is physically impossible. When current flows through a straight metallic conductor, it generates a magnetic field consisting of concentric circular lines centered on the wire. The direction of this field is determined by the right-hand thumb rule, which states that if you point your right thumb in the direction of the current, your wrapped fingers show the direction of the magnetic field. A solenoid is a long coil containing many circular turns of insulated copper wire wrapped closely in the shape of a cylinder. When current passes through a solenoid, it behaves exactly like a bar magnet, producing a uniform magnetic field inside the coil represented by parallel straight lines. A current-carrying conductor placed in a magnetic field experiences a mechanical force because the magnetic field of the conductor interacts with the external magnetic field. The force is maximum when the direction of current is perpendicular to the magnetic field. We determine the direction of this force using Fleming's left-hand rule. If you stretch the thumb, forefinger, and middle finger of your left hand mutually perpendicular to each other, such that the forefinger points in the direction of the magnetic field and the middle finger points in the direction of the current, then the thumb will point in the direction of the motion or force acting on the conductor. An electric motor is a rotating device that converts electrical energy into mechanical energy. It operates on the principle that a current-carrying rectangular coil placed in a magnetic field experiences a torque, which rotates the coil continuously using a commutator ring to reverse the current direction. Direct current, or DC, flows in only one direction, such as current from chemical batteries. Alternating current, or AC, reverses its direction of flow periodically. In India, alternating current changes direction 50 times per second, meaning its frequency is 50 Hz. The main advantage of alternating current over direct current is that electric power can be transmitted over long distances with minimal energy loss. Electromagnetic induction is the phenomenon of producing an induced current in a closed-circuit loop by changing the magnetic flux linked with the loop. This was discovered by Michael Faraday. The direction of the induced current is given by Fleming's right-hand rule. An electric generator is a device that converts mechanical energy into electrical energy using electromagnetic induction. By rotating a coil in a magnetic field, the changing magnetic flux induces an electric current that can be drawn to power external circuits. Generators can be designed to produce either alternating current or direct current, forming the basis of global electrical power grids. In our homes, we receive electric power through a domestic circuit consisting of 3 wires. The live wire, usually red, has a potential of 220 volts. The neutral wire, usually black, completes the circuit. The earth wire, usually green, is connected to a metal plate buried deep in the earth near the house, serving as a safety measure for metallic body appliances. All home appliances are connected in parallel so that they receive the same voltage and can operate independently. Safety devices include fuses and miniature circuit breakers, which protect appliances from damage due to short-circuiting or overloading by melting or tripping to break the circuit. In this comprehensive physics lecture, we have studied the effects of electric current and electromagnetism. We explored electric current, potential difference, and Ohm's law, detailing how resistance varies with length and area. We calculated equivalent values for series and parallel resistor combinations. We investigated Joule heating and electric power formulas. We analyzed the magnetic fields produced by straight wires and solenoids, using the right-hand thumb rule. We detailed the force on a conductor using Fleming's left-hand rule, which governs electric motors. Finally, we studied electromagnetic induction in generators and domestic circuit safety. Mastering these concepts is essential for modern electrical engineering. To ensure absolute mastery of this academic unit, let us conduct a comprehensive review of the core concepts and frameworks we have explored today. The key to solving complex problems lies in first understanding the fundamental definitions and structural relationships between variables. Whether you are balancing chemical equations, analyzing geometric properties of circles, or deriving logarithmic equations, you must always verify the base rules, identify the known variables, and state the governing principles explicitly before proceeding. Remember, active learning is not just about memorizing equations. It is about recognizing how these equations model real-world phenomena. In the next slide, we will look at an advanced practice problem designed to challenge your analytical thinking and test your application of these concepts. Practice writing down the definitions and drawing the visual models from memory to solidify your comprehension.